Good afternoon to everyone. I welcome all of you to the 61st lecture in the lecture series in nonlinear dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, India. I'm happy to introduce today's speaker, Professor Ralph Andrzejak from Department of Information and Communication Technologies, Pompeu Fabra University, Barcelona, Spain. Professor Andrzejak obtained his PhD in the year 2001 at the University of Bonn, Germany. He carried out his first postdoctoral work at the Research Center Julia, Germany, about 2 years, and continued his second postdoctoral work at the Computational Neuroscience Group in Universitat Pompeu Fabra, Barcelona, Spain, about an year. Subsequently, he got a tenure track position in the same department and worked in this position about 4 years. He then appointed as an associate professor in the same department in the year 2011 and elevated as full professor in the year 2018. For the past 15 years or so, he is serving at the Department of Information and Communication Technologies, Universitat Pompeu Fabra, Barcelona, Spain, in various capacities. Professor Andrzejak is carrying out research at the interface between physics, applied mathematics, and neuroscience. In particular, he is showing interest to develop innovative nonlinear time series analysis techniques. He also investigates coupled oscillator network models that show chimera states. Professor Andrzejak has published several notable works in nonlinear time series analysis, chimera states, and synchronization, and acquired around 8,000 citations and possessing very high H index. With several students carried out bachelor's and master's theses under his guidance. He has also acted as PhD supervisor for several students. With this short introduction, now I invite Professor Andrzejak to start his lecture. Over to you, Professor.
Okay, thank you very much. One last time, can everyone hear me well?
Yes.
Okay, very good. Then I would like to start by thanking the organizers of this lecture series. It's really very impressive that you organize this very long series of lectures, thereby providing your students with an overview to research which is done in all over the world. So I congratulate you for this great initiative. That's truly something to be appreciated.
Okay,
Indeed, my own background is physics. I studied physics in Bonn, and then I worked at the Department of Epileptology, so a hospital where patients with epilepsy are treated, and I dedicated myself to the analysis of signals measured from epilepsy patients. And more recently, I started working on these models, which I will talk about today. And so in particular, what I would like to do today is that I would like to, like already announced in the title, I would like to build a bridge between the fractal geometry of the Mandelbrot set and the dynamics of partial synchronization in chimera states. And I assume that most of you might not be familiar with the Mandelbrot set, and also most of you might not be familiar with chimera states, and therefore I will give a brief introduction to these two concepts in this lecture. To begin with, what both have in common is that they can be generated by very simple mathematical models. So we can use very simple mathematical models to generate quite complex dynamics and to generate quite complex patterns. And as we will see, I can also use a very simple mathematical model to establish a link between the two. So let me start with the Mandelbrot set, and let me briefly remind you about the Mandelbrot set. It was in the 80s of the past century when it became famous much beyond mathematics. So here, for example, it was featured on this journal called Scientific American in 1985. And when we go to the scientific article of Mandelbrot, and we look at his references at the time, so this article was published in 1980, and here we see some of the references of this article at the time, we can see that actually some of the fundamental references of this article date back to the beginning of the past century. Here we have this work by these French mathematicians Fractal and Julia, and as you can see, this dates back to the beginning of the 20th century. So this has a long history to it. And like I said in the beginning, what is fascinating is that we can generate the Mandelbrot set with a very simple equation. And in fact, all we need is this quadratic map, which we have written down here. So it's very straightforward. So in order to get your state at time n+1, you take your state at time n to the power of 2, and you add a parameter c. So time is discrete. So time is measured in discrete steps. That's why it's called a map, which is different from a differential equation where time is quasi-continuous. And now, like I said in the beginning, I would like to establish a link between the fractal geometry of the Mandelbrot set and the dynamics of chimera states. And therefore, what I will do, I will look at the dynamics generated by this map, which allows to generate the Mandelbrot set. So this map is generating the Mandelbrot set, and I want to build a bridge between the Mandelbrot set and the dynamics of chimera states. So what I will do is I will look at the dynamics of this map. And therefore, what I do here is that I plot the first few states of this map for some exemplary value of this parameter c. Now, as you can see, this parameter c is complex valued, and therefore also the states of the map will evolve in the complex plane. And what we see here are the first few states of this map. So here you can see the initial state in black, which I set to the origin of the complex plane. This is a definition. So we choose the initial condition in the origin of the complex plane. And then we start the iteration, and we then get the red state, the blue state, the green state. Now let me add some more states. And we can see that we get this triangular pathway, right? So we go from this red branch to the blue branch to the green branch, and then back to the red branch. And now looking at it, it doesn't seem to be strictly periodic, but it seems to go towards the center. And this is confirmed once I plot all states for time to infinity. So that is what I do now. And now let me take away the symbols and lines which are used for the initial states. And then we can see that indeed we converge to a fixed point here in the center. So what happens is that you go to the red branch, so to say. Your next iterate is in the blue branch, your next iterate is in the green branch, your next is in the red one, and so on and so forth. And while going from one branch to the other, you more and more approach the center here, the fixed point, which you have sitting here, right? So here we get a solution which converges to a fixed point. Now what I will do in my next example is that I will slightly change the value of this parameter c. So as you can see now, the value of this parameter c is changing, and now I will use the same sequence of images like I used before. I look at the first 3 states, then I look at some more states, and now I look at all states for time to infinity, right? And we can again see that the dynamics is converging to a fixed point in the center. The convergence is slower as compared to what we had before. So that is my first example, which you had seen before. That is my second example, and you see here the convergence is slower. Again, I change the value of my parameter c, and then you see that the convergence is getting even slower, right? So we see that it really takes a long time for the states to converge to the fixed point, which is still sitting here in the center of my plot, right? Now, something different will happen. I again change my value of this parameter c. And now, if you look at the temporal sequence of these states, what you will see is that there's no attraction from the center any longer. There's no stable fixed point sitting in the center any longer. And instead, what the dynamics do, if you look at the temporal evolution, so here we only look at a snapshot, so you cannot really appreciate it. But let me tell you that if you look at the temporal evolution, you see that the dynamics is moving inside out. So it's moving from the center towards the periphery. From the center, it's moving towards the periphery. Once it has reached the periphery, so the outer region, then the dynamics is re-injected into the center. And then it starts again to move inside out. At some point, however, the dynamics is not re-injected to the center, but it's escaping to infinity. So here we get a solution which is non-bounded, but escapes to infinity instead. When we again change the parameter, we see that we get a similar scenario, but now the escape to infinity is much faster. So it takes much fewer iterates to just go to infinity. Again, so I keep on changing the value of this parameter c, and the next thing which I find is this one. So here we see quite long transients, and then we go to a period 3 orbit. So we see that eventually we go, after these initial transients have faded out, we go from here to here to here to here. So we now enter into a period 3 orbit. In the next example, we see, okay, we get a dynamics where we also go to a period 3 orbit, but much faster. And please recall one more time what these colors represent. So I'm looking at the dynamics of one map. I'm looking at the dynamics of one map. The point is that it now goes in the period 3 orbit. So it goes from the red branch to the blue branch to the green branch and so on. And what you see in the outer area are transients. Once they have faded out, it just goes from this spot here to this spot here to this spot here and so on. So what we have seen so far is that depending on the value of this parameter c, we get qualitatively different behavior. We saw that we found convergence to a fixed point. We saw dynamics which escape to infinity, and now we see dynamics which converge to a period 3 orbit. And we also saw that the time it takes the system to settle down is different. We saw very fast convergence, we saw slow convergence, we saw a fast escape to infinity, a slow escape to infinity, and we saw a rich variety of different dynamics. But so far I only showed you a series of a handful of examples, and what we should do now is we should vary this parameter c quasi-continuously in the complex plane, because this will allow us to draw a phase diagram of the dynamics of this map independent on this complex parameter c. And as you will have anticipated, those of you who know this Mandelbrot set, this leads us to this famous Mandelbrot set, which I've plotted up here. And here I zoom into this, or down here, I should say, I zoom into this square, which we have up here. So where are we? We are still in the complex plane, but now we are no longer in the domain of the states of the map like we were when we were looking at the dynamics, but instead we are in the domain of this complex parameter c. And now, if for a given value of c, we find that the dynamics is escaping to infinity, we draw a gray pixel. And you may not see the different shades of gray in the upper plot because of the transmission via Google Meet, but there are different degrees of gray, and a dark gray means that the escape to infinity is very quick, and a light gray means that the escape to infinity takes longer. Now, if in contrast we find that we remain bounded, that we do not escape to infinity, we use a non-gray color. And here we use the non-gray color to indicate the periodicity of the resulting dynamics. And in the example which I showed you before, I went along this little red pointer here. So that's why at first we saw convergence to a fixed point corresponding to period 1. Then I crossed this little gray bridge. Please recall that we use gray colors when we have dynamics which escape to infinity. And then we entered into this region where we have a period 3 orbit. And as you can see, in other regions, we would find dynamics of much higher periods. You can see, or you cannot really see, but you can guess that from these more reddish colors that here in these areas we would get dynamics with much higher periods. Okay, and this basically now, or like if we would now zoom into these areas, we would find fascinating fractal structures on all spatial scales. And that is a famous fractal geometry of the Mandelbrot set. Okay, and with this we have our first part, because now we have reminded ourselves on how to generate the fractal geometry of the Mandelbrot set. And now I can give you a little bit of background on these chimera states. So chimera states were first described by Kuramoto and Batoktok in the year 2002 in this article published here. And the name chimera states was then introduced 2 years later by Abrams and Strogatz. And initially chimera states were observed for a ring-shaped network of all identical, non-locally coupled, time-continuous oscillators. That was the first setting in which these chimera states were studied. And later, this concept was generalized in many different ways. Now, what is the basic feature of a chimera state? So imagine you have a network of all identical nodes. Your nodes are all the same. And also, the coupling between the nodes is the same between all of them. So all your nodes are the same, and they're all in the same arrangement. They all see the same environment. Now, since all nodes are the same and they are all in the same situation, in principle, one might expect that qualitatively they should all show the same behavior, right? And in particular, when it comes to synchronization, the nodes should either all synchronize or they should all desynchronize. However, for chimera states, this expectation is not fulfilled. For chimera states, despite that all nodes are the same, the network falls apart into two different groups. One group of oscillators which is synchronized and one group of oscillators which is desynchronized. And this coexistence of synchronization and desynchronization, this coexistence of parts which don't really fit together, also motivated the term chimera state, because in Greek mythology, a chimera is this monster which consists of parts of different animals which also do not really fit together. And that is why Abrams and Strogatz proposed the name of chimera states for this phenomenon. Okay, now, as we can see from the titles of these papers, we will need some coupling in order to get chimera states. And therefore, what we need to do now is that we go from one map. Everything which I've shown you before was based on one individual map. And now what we will do is we will go to a network of coupled maps. So what we do is, instead of using just one map, we will be using 4 maps. And now, before I use the colors to encode different branches in the dynamics of one map, and now I will use the colors to encode the different maps, to represent the different maps. So you use a total of 4 maps, and your 4 maps are all identical. So they all have the same value of C, and they all follow the same equation. And now you couple these 4 maps, and I will show you the equation of the coupling in just a minute. But for the moment, let's just assume that we connect the maps. So, and they're all to all connected. But by the strength of the coupling, we implement a topology of 2 pairs of 2 maps each. So we have the red-black pair, and we have the green-blue pair. And the coupling within the first pair, red-black, and within the second pair, green-blue, is stronger than the coupling across the pair. So these pointers are meant to indicate the coupling. Now let me briefly show you what I mean by the coupling in terms of equations. It's very simple. So these look like long equations, but they are very simple because they all follow the same logic. So the first map has its own dynamics. The map U has its own dynamics. Then you see that I'm using the difference with the map in its own pair with the coupling strength CW, because it only has one partner in its own pair, and then I use the differences to the maps in the other pair with another coupling strength CA, right? And importantly, the CW is stronger than the CA. And now we can now go ahead and look at the dynamics of this network of maps. And I will start with the first map, which I here depict in red. And we can see it has some nice transients, but then it also goes to a fixed point sitting here in the center. So the convergence is so slow that the fixed point looks almost like a compact disk in the center, but let me assure you that it really goes to a point. And now let's have a look at the dynamics of the second map, which we here plot in black. And one more time, so these maps are all identical. They all have the same value of C. Like before, in my different examples, I will be using different values of C, but within one example, the value of C is always the same for all four maps. So now let's look at the dynamics of the second map, and we can see that also the second map is converging to a fixed point. The transients look different, but it's converging to a fixed point. And so does the third map, and so does map number 4. They all go to a fixed point. Now, these four maps, they are coupled together and they evolve together, so it makes sense to plot them together in the same graph. And once we do that, we can appreciate that they all go to the same fixed point. They all go to the same fixed point sitting here in the center of our plot. Now you might say, well, and therefore we get a fully synchronized solution of these four maps. On the other hand, if you work in dynamical systems and you study synchronization, you might say, wait a moment, if you want to talk about synchronization, you need some motion, right? And here there is no motion any longer. The four maps just go to the same fixed point, and then they're sitting there. There's no motion. So this should not be considered as synchronization. But this will be different in my next example. So now again, I'm in the sequence of the examples, I will be changing the value of C, which is always one more time the same for all four maps. And we start by looking at the first map. And again, we go to a period 3 orbit. So after these initial transients, which you see here faded out, it just goes from here to here to here and so on. So we are in a period 3 orbit. Now let's look at the motion of the second map of the first pair, and we can see that it also goes to a period 3 motion. It looks quite similar, in fact. The initial transients of the third map, they look different. The green one, they look different, but they also go to a period 3 orbit, and so does the blue map. And once we plot all four maps together, we can appreciate that they all go to the same period 3 orbit. So they all have different initial transients, but then they go in full synchronization from here to here to here to here and so on. So here we get a perfectly synchronized period 3 motion. And if we think about it, that makes sense, right? Because we have a network of four maps. They're all identical and they are all-to-all coupled. So, and as a consequence of the coupling, well, they enter into a fully synchronized motion. That makes perfect sense. It will be slightly different in my next example. So here, again, I start with the first map. It looks a little bit strange here, but if we zoom in, we will see that it just makes some extra loops before it finally settles down to its period 3 orbit. And if we look at the second map of the first pair, we again see it looks quite similar. Initial transients look different, but it also goes to a period 3 orbit. Now comes something different. The green map, the first map of the second pair, also goes to a period 3 orbit, but apparently to a different period 3 orbit. And so does the blue map, the second map of the second pair. Now, if we plot all four maps together, we can see, indeed, we get synchronization within or between the red and the black map. They go together from here to here to here to here and so on. And we get synchronization within the second pair, within the blue-green pair. They go together from here to here to here. So we get within pair synchronization, but we do not get across pair synchronization, right? There's no synchronization between the red-black pair and the green-blue pair. And again, if you think about it, this within pair synchronization makes sense because the coupling strengths within the first pair, or I should say the coupling strengths within pairs is stronger than the coupling strengths across pairs. So the coupling between red and black and the coupling between green and blue is stronger as compared to these across couplings. And therefore, this within pair synchronization is somehow reflecting the architecture of our network, right? But this will be different in our next example, because now we can see that the symmetry of the network structure, the symmetry of the architecture is broken by the dynamics. Let me go directly to the superposition of all four dynamics, where we can now see that we get, again, synchronization between red and black. So after transients have faded out, they go together from here to here to here and so on. So we get synchronization within the first pair, but we do not get synchronization within the second pair. So you see that also the green and the blue maps, they enter into a period 3 orbit, but they do not synchronize, right? And that is a chimera state. So you have these four identical maps with the symmetric arrangement of the coupling, but then the dynamics decides that, well, the first pair goes in synchronization and the second pair goes in desynchronization, right? And this coexistence of synchronization and desynchronization in a network of all identical maps, that is a chimera state, right? Okay, and now our last example in this sequence of examples shows that also for this network of coupled maps, we can get solutions which escape to infinity. Here it was the black map which escaped to infinity first, and please recall that the coupling is aiming to synchronize these maps, and if one of the map goes to infinity, it will just pull the other maps to infinity as well. And so here, also in this case, we can get solutions which escape to infinity. Okay, in the next block, we should do something very similar to what we have done for one map before. Because again, we will go to the domain of this complex parameter C, and then we will draw a phase diagram of the underlying dynamics, but now no longer for one individual map, but for these four coupled maps, for the dynamics of these four coupled maps. And again, if we find that our dynamics escapes to infinity, we draw a gray pixel, and the faster the escape, the darker the gray. If in contrast, we find that our dynamics remains bounded, we use a non-gray color. And now these non-gray colors indicate the different states of synchronization or partial synchronization. And the states depicted here in light blue show that for these values of the parameter, we get fully synchronized solutions. So here, all four maps enter into full synchronization. The other extreme are states which are fully desynchronized, and this is shown by red. So I didn't show you an example for fully desynchronized dynamics, but we can also get fully desynchronized dynamics. And then yet another state of partial synchronization is a cross-pair synchronization, and that is shown here in green. Now you might wonder, there were some other states which we have not included here, but we will see them in just a second. Now, if you see this from the global scale and you know the Mandelbrot set, you might say, well, but that looks very similar like a Mandelbrot set, very similar to a Mandelbrot set. The periphery, the surroundings, they seem a little bit perturbed, and if you look into some of the details, they seem a little bit like changed. So maybe everything which I have achieved by using four maps instead of just an individual map is to generate like a perturbed, like a noisy version of the Mandelbrot set. But now let me zoom into this pattern in order to convince you that this is totally not the case. So I start by zooming into this area here, into this square here, and I get this image. containing these attachments to the main body of the Mandelbrot set, and then I continue to zoom into this square which I have here, resulting in this image here. And at this scale, we can already appreciate some of the main features of this fractal which we are seeing, because recall that here, this blue color corresponds to parameter values for which we get full synchronization of all 4 maps. And here these red colors correspond to parameter values for which we get full desynchronization of all 4 maps. And now we can also see that the connection between these 2 areas is obstructed by what we call these gray ridges of instability, because recall that we use gray colors for parameter values where the dynamics escapes to infinity, right? So these are these gray ridges of instability. And between them, we find what we call lakes of stability. And here, for example, you see a big green lake of stability containing parameter values for which we get a cross-pair synchronization. Here you also see smaller yellow lakes of stability for which we get within pair synchronization. And last but not least, these purple lakes, they correspond to chimera states. These were these peculiar states for which we get the symmetry-broken dynamics. Okay, and now we can continue to zoom in, and we zoom into this square here, resulting in this image. And when I saw this image first, I thought that maybe what we have here, maybe something went wrong. Maybe I didn't use enough iterations to generate this image, because it seemed to me as if we here had some artifact. So, well, what we can do is we can zoom in and see what happens. And that is what we get. Totally not an artifact. Everything is correct. So what you see is here, you have this on this scale, big purple lake of stability. And then this big lake of stability is filled from below by these gray instabilities. And this peculiar light gray indicates that here in this region, the network undergoes particularly long transients before it decides to escape to infinity. And then these instabilities are like perforated by countless lakes of stability, which you can see here. And what looked from a distance like an artifact, that was what somehow seemed strange from a distance, turns out to be a structure which strongly resembles the main attachment in the classical Mandelbrot set. Okay, and now we continue our journey and zoom into this area here, resulting in this image. And now there are many questions which you could ask. And among them is, for example, do these different lakes of stability flow together? Because here it may seem, for example, that let's say the purple lake and the green lake, they are in contact, they flow together. And in order to find an answer to this question, well, we can zoom in and see what we get. And the answer is no. So these different lakes of stability, which contain parameter values leading to different states of partial synchronization or full synchronization or full desynchronization, these different lakes of stability are always separated by these gray ridges of instability. So they are never in direct contact. Okay, and one last zoom step leading to this image here. Okay, what we have done so far is that we iteratively zoomed into the same area of this fractal. And what I will do now, let's have a quick look into some other areas of this fractal. So let's go back to the global scale, and let's look into this area, and let's see what we have here. So I zoom into now here into this area. And to me, very often we can find patterns in this fractal which somehow resemble things with which we are familiar with from nature. And here, I would say, to me, this looks almost like lava coming from a volcano, the way in which these instabilities here invade this lake of stability, right? So it somehow looks as if we were close to a volcano, which is sending the lava into the sea here. Another example is this one, which in a sense allows to illustrate some curious non-locality of these patterns. So here you see this big blue lake of stability, and just opposite to it, you see this spiral-like arrangement of instabilities and stabilities. And if you look closely, you see them everywhere. You see it here on the big scale, but then you also see it here and here. You see it here and here. You see it here and here. The more you look, you find them everywhere, because you're in a fractal and you have scale invariance. So you see this pattern repeating on all spatial scales. So in a sense, this presence of the stability here is inducing this peculiar arrangement of stability and instability just opposite to it. Okay, and now coming relatively close to the end. So there's still something to be presented, but I'm approaching the end of this presentation. That's another pattern which we find somewhere else, and very often we find these spiral-like structures, right? And so let's zoom into one of these spirals. And now you might wonder, okay, I see a spiral, and there are blue colors, there are yellow colors, and there are gray colors. What is in the center of the spiral? There will be a point, right? There's a point in the center of the spiral, and it will belong to one of the different sets. And now we might wonder, well, is it a yellow point, a blue point, or a gray point? Well, let's do what we have done before, and let's zoom in. First zoom step, second zoom step, but now we will say, wait, this will not work because you will never be able to resolve the center of a fractal spiral by zooming in. It would just always be a spiral, right? So you cannot find the point in the center of a spiral. And then if you decide to zoom into one of the branches instead, you might not see the square here on the resolution of your screens, but here's another zoom square where we zoom into now. And then if you zoom into there, you again find a different structure of something which you haven't seen anywhere else before. And please look at this detail here, this spiral which you see here. And let me zoom out again. Let me zoom out and see where we came from initially. That's where we came from initially. And look at this structure here of this spiral. And now I zoom in again, so I go into smaller scales, right? And you see it looks very similar here. Okay, now let me briefly summarize technically what I have shown you. So you have this map, which if you have one map, it just either it escapes to infinity or it remains bounded. And if you draw the states which remain bounded and the states which go to infinity in the plane of the complex parameter C, you will get the famous Mandelbrot set. Now what we do is we take 4 of these maps, which are all identical, and which we arrange in this architecture, where by means of the coupling strengths, we induce a 2-pair architecture, right? So we have the black-red pair and the green-blue pair. And you could also say that this is a network of 2 populations where we use the minimal size of 2 for each population. And now, depending on this parameter value C, which is the same for all 4 maps, you get qualitatively different solutions. You find solutions which are fully synchronized, you find solutions which are fully desynchronized, and you find solutions which are only partially synchronized. And among them, you find this chimera state where, despite that your network is fully symmetric, one of your pairs is synchronized and the other pair is desynchronized. That was this chimera state. And last but not least, you also find solutions which escape to infinity. And a very important finding here is that the boundaries between these different states in the domain of this complex parameter C, they form these fascinating fractal patterns. So the Mandelbrot set, you have just fractal boundaries between convergence and divergence, and here you also have fractal boundaries between these different states of synchronization and partial synchronization. Okay, and now I would like to end with some non-technical remarks about these patterns. And please recall that the term chimera state was motivated by this monster from Greek mythology, consisting of these different animals. Now, if you ask me, the creatures which we may see in these patterns, I would say they look at least as scary as this original chimera monster from Greek mythology. Okay, another example is this one. So again, this is an iterative zoom. And in the main presentation, I showed you what we can find when we zoom in here, and now we zoom in here instead. So you have to read it from left to right and from top to bottom, and then you see the sequence of images. And then I came across this image, and which I now show you in an enlarged version. And I'm not sure, so it reminded me of a cartoon creature, a personality in a cartoon. And I'm not sure if this cartoon was also published in your country, but this cartoon is quite famous in Europe. So when I was a child, many years ago, there was this cartoon character, this one here, which also has these very long tails. And when you look at this image here in this fractal, it somehow reminded me of this cartoon character. Now, of course, I do not know if this cartoon character was published in India. Maybe you can tell me in the discussion, right? Then another example is this one. So, like I said before, very often we find patterns that somehow resemble things which we find in nature. And so here, this again reminded me of lava, which we see here on the left-hand side. But then there's something more to it. So it also somehow resembles ice, right? So, and maybe here we could say that this fractal image is like the coexistence of fire and ice, also two things which do not really fit together, just like the different parts of chimeras. And now I could continue showing you many more examples of these images, but let me better stop here, because otherwise we could continue, like I said, forever. And let me only announce that this study, the whole story, was published in Chaos last year. I wrote this paper during the COVID confinement, so I had to do it on my own. I was working in my home alone, so that's why I'm the only author of this paper. And if you go to our homepage, so if you Google my complicated last name, you will find that there's a PDF of this paper, if you're interested in reading the full story. And with this, I would like to thank you for your kind attention. I would like to again thank the organizer of this seminar lecture series for this organization. And like I said before, it's a great initiative which allows your students to be in direct contact with the research that happens across our globe. Thank you very much indeed.
Thank you, Professor. Thank you. So this forum is now open for questions, clarifications, doubts. Questions from the audience?
You can type them in the chat if you want to, or you can also open your microphone and just raise your question. Then maybe let me ask you a question, because so I was wondering, who of you knew the Mandelbrot set beforehand? Is that something you're familiar with? So I assume that you are in your undergraduate degree. Maybe some of you are in your master program. Is this set known to you?
Yeah, some of the research scholars, they study in the coursework.
Okay. Mm-hmm.
The coursework they study, they come across this Mandelbrot set.
Okay, very good. Mm-hmm. So maybe, you do the actual implementation of it?
So I have a couple of questions.
Yes, please.
So people are talking about lots of states in the chimera studies.
That's true.
Status. So you have also come across different kinds of states, except this synchronized, desynchronized states. Some other kinds of states.
That's very true indeed. That's very true indeed. So, like I said in the beginning, chimera states were at first introduced in a ring network of all identical time continuous oscillators. That was in this paper by Kuramoto and Bartok. And they basically, you had like one group of oscillators which was going with a high coherence, and another group of oscillators which were detached and were incoherent. They were not coherent among them, and they were also not coherent to the rest of the oscillators. That was an initial setting. And later, this was studied in many, many different settings. So people, instead of using time continuous oscillators, they used maps like we do here, but also different architectures and multi-layers, and therefore all different types of chimera states were found. And you find many, many names, such as amplitude chimeras or phase chimeras. Also, you can find solitary states. And so the more complex you make your system, the more complex can be the solutions which you get. Now, the idea here with this paper was also to say, okay, let's reduce it to the most simple setting we can think of. Because all we have here are just four maps, which is the minimal number to have 2 plus 2, because then 2 can synchronize and 2 can desynchronize. So here, in a sense, we go to the smallest possible setting where we can observe these chimera states. But if you allow for general settings, you can find like a countless number of different chimera states.
Are you able to read the chat box? There is a question.
Yes, I saw that there was a question. I have to activate the chat again. I'm using, hold on, let me.
The last one.
Yes, thank you for this question. So if I understand your question correctly, it's about predicting different types of chimeras, like iterant or itinerant chimeras. That depends always on the system we are studying. So, for example, here in this very simple system, we can only get the states which we had. We can get full synchronization, full desynchronization, with in-pair synchronization, a cross-pair synchronization, and the chimera states. That's it. We cannot get more. In different architectures, we know beforehand that we can get different types of chimera states. So, for example, if you have ring models of maps, they can be symmetry broken with regard to the phase or with regard to the amplitude, and you know then from your experience that different types, different network architectures allow you to generate different types of chimeras. And there are also things, for example, you know that if you use a very narrow kernel for the mutual coupling, you can get chimera states with not only one pair of coherent and incoherent groups, but with several pairs of coherent and incoherent groups. But sometimes you really have to try. So you set up a new dynamics, and then there's a certain surprise of what type of dynamics you get. So it's not always fully predictable. I'm not sure if this really answered your question. If this did not answer your question, please feel free to write again.
Tamilarsan, is that clear? Yes. Yes. Professor Upataya, do you have some doubts? Do you need some clarification, sir?
Say it again.
No, I'm asking the participant.
Okay.
Whether he has any doubt. So in your studies, you consider two populations, right? Two populations.
That's correct.
Yeah. So you can also consider 3 population network, right? Like that. You can extend.
That would be a very interesting question, something which we haven't looked into before. And this is truly a very relevant question. What we did was that we used different sizes of population. So here I used 2 pairs of just 2 maps. What we also did was using 2 pairs of 3 maps, or 2 pairs of 100 maps each. But this is the size of populations, but always using 2 populations. But what you're proposing would be very, very interesting. So to use not 2, but 3 pairs or 3 populations. That's something very, very interesting. So there would be many, many questions which we could study. For example, there's the concept of relay synchronization, so that you have population 1, population 2, population 3. They are one behind the other. And so population 1 and 3, they are not really connected, but they still can synchronize via interacting with through population 2. Mm. So that could be something that we could look into following your proposal.
Okay, thank you. Sir, do you have some doubts, sir?
No, thanks.
Okay, thanks. So any other questions from the audience? Okay, we are not getting any question.
Okay, as you said, so if your students are implementing that in their coursework, right?
Yeah, so if they study Mandelbrot in their coursework, because they study nonlinear dynamics as the coursework paper.
Oh, okay. So in case you want to study this network, if you go to our homepage, you will find the source code for this network. It's straightforward, but still you have to think about how to implement it. So if you're interested, please feel free to go to our homepage and get the source code, and please feel free to get back to us in case you have doubts on how to implement it. I have to warn you, it's a little bit time consuming, the actual computation, but you can get very interesting results.
Okay. I will ask my students to look into your homepage there. Look into it.
Very good.
All right. So since there are no more questions, I would like to conclude the session by thanking Professor Ralph Andrzejak for accepting our invitation and giving a very interesting talk on the chimera states. Thank you, Professor. Thank you.
Thank you very much. Thank you very much for your invitation. Thanks for your attention. And have a nice evening in India. For me now it's 1 o'clock, and I will now go to my university where I have to teach in the afternoon. But for me, still, it's a long day ahead. I know that. What time is it now? In
4:30.
Okay. Very good. For me, the remaining day is still longer.
Okay.
Okay. Thank you very much.
Good afternoon, Professor. Good afternoon.
Okay. Bye.
Bye.